All right, my name is Harsh Akanuri, and I'm a senior.
I'm Nathan Zhang. I'm also a senior.
I'm Olivia May. I'm also a senior.
I'm Timothy Wu, and I'm a senior.
I'm Kevin Zhang, and I'm the token junior.
Okay, so go ahead whenever you're ready.
All right, so hello everyone. We're at Livingston High School, and we're here to present our solution to this year's M3 challenge problem. So in terms of our overview, our solution consisted of a variety of models to address the crux of the problem. So in our first problem, we analyzed supply and demand factors of housing and developed a regression model to predict the number of housing housing units in Albuquerque, New Mexico, and Seattle, Washington over the next 50 years. And then in the second problem, we developed a state function that maps out the movement of individuals across various states of homelessness to predict the homeless populations in both cities over the next 5 decades. And finally, we developed a robust long-term plan to help combat homelessness through testing the plan under state function model of the homeless population. So for the first problem, we created random forest regression models, one for Albuquerque, New Mexico, and one for Seattle, Washington, that operate on 3 crucial features that predict the housing supply in both of these cities over the next 50 years. We made 4 key assumptions that allow our model to work. Our first assumption is that no major technological advancements that impact the growth of housing supply in either city are made, and we assumed this since the growth of technological advancements is quite unpredictable, and thus we thought it was unreasonable to include in our model. Next, we assumed that the 3 factors we used in our model were functions of time. This allowed us to predict the values of the 3 factors in 10, 20, and 50 years and input it into a random forest regression model to get the numbers for the housing supply in those many years, respectively. Our third assumption is that housing supply could be measured as the number of housing units in each city, since we thought that was a fitting metric for the term housing supply. And our final assumption is that both cities would have sufficient physical resources to build housing units, and we decided not to take into account a lack of resources as a factor in order to simplify our model and isolate the 3 variables of interest that we considered. So our regression model utilized 3 components to actively determine the number of housing units in each city. The first factor in a regression model is population, which accounts for the natural demand of housing units in each city. Next, we included unemployment rate as our second factor, as an indicator of the likelihood of real estate investors to finance a housing supply production in the cities. Unemployment rate also accounts for the percentage of people that might not be able to afford housing. Our final factor, median income, acts as an indicator of the economic standing of each city, as well as the affordability of housing for the citizens. And as the median income of a city increases, it is likely that the demand for housing will also increase as the purchasing power of the citizens goes up. So combining those 3 components constitutes a framework for our solution to the first problem. And we also understood that in order to determine the housing supply over the next 5 decades, we had to adjust our regression factors accordingly with time. With data on population, median income, and unemployment rate from the US Census, in each of these cities, we performed regression on these variables with respect to time. And for both of these cities, we decided to use polynomial regression for 2 features, unemployment rate and median income, and use logistic regression for population. And all of the values predicted by these regression in 10, 20, and 50 years were used in our random forest regression models.
To model the housing supply over time, we trained a random forest regression model, a machine learning algorithm on a dataset of Albuquerque and Seattle with population, unemployment rate, and median income over 10 years. In regard to concern with extrapolation using the random forest regression model, we also used a stacking method with a standard linear regression model using the same factors to ensure reliable predictions on future values. The random forest works by creating a set of decision trees, each of which creates a series of logical splits that maximize information gain and minimize error in order to predict the housing supply. The outputs of the individual trees are averaged for the final ensemble prediction. By following the splits created during training, our model is able to produce a regression output for new data points. And our model consists of 10 decision trees, each limited to a maximum depth of 5 nodes to improve generalization of unseen data. So there are a few major strengths with using a random forest model. First of all, the random forest model is adept at capturing nonlinear relationships like housing supply. Unlike linear regression models, decision trees can naturally capture nonlinear interactions between features without needing explicit specifications. This is because of the use of feature subspace selection, where the random forest trains each individual decision tree on different random subsets of the data. This process ensures variability between trees, thus reducing the effect of multicollinearity and allows the model to determine optimal splits regardless of nonlinear or unwanted relationships. Also, since we only consider 3 important factors when predicting housing supply, our model can be easily generalized to other cities. And additionally, outliers and noisy observations have minimal influence on overall predictions because the random forest model considers multiple trees rather than relying on a single model. So there are some potential weaknesses, including the lack of a large data set. So due to time constraints, we're unable to find complete data on the factors we used for more than 13 consecutive years. Also, because the random forest model obtains predictions through backend algorithms and arithmetic, it is difficult to use it for qualitative analysis of the housing supply problem. Regardless, we are able to experiment with factor values to quantitatively analyze how the random forest model weighs each factor and importance when making decisions. And finally, as with any mathematical model or artificial intelligence framework, predictions on a complex problem like housing supply will decrease in reliability and confidence as years in the future increase. So ultimately, the model predicted sizable increases in housing supply for each time period in both cities, as shown in the table, and these predictions are consistent with expected results and can be attributed to population increases and economic growth.
To determine the cause behind their homelessness, we use the following assumptions illustrated by our flowchart. From the perspective of someone who is already homeless, we examine their drug use history. In the case that they have prior history with drug use, then we consider drug addiction to be the cause. If not, then we question whether or not they have a history of mental illness. If yes, then we consider mental illness the cause. If not, then we question if they have a history of domestic violence. If so, then we treat domestic violence as the cause. However, if all the following cases return false, then we default that the cause of homelessness was poverty. Additionally, we're disregarding the population within shelters. Most homeless shelters located within the U.S. have baseline requirements of their inhabitants. And so we can assume that while in shelters, they are neither addicted to drugs nor are mentally ill. Furthermore, to simplify our system, we assume that only drug-addicted homeless people die. Deaths resulting from other causes are insignificant in comparison.
Given these assumptions, we're able to create a state function that accounts for 6 states of people: drug-addicted homeless people, mentally ill homeless people, unafflicted homeless people, victims of domestic violence, and poor people and dead people. We can find statistics on the proportions of people in these categories, as well as the relative change between categories each year using the average duration of homelessness of 40 months to determine change across 12 months. We're using a stochastic model, so we only consider what happens on December 31st. Because of the clean nature of shelters, we consider homeless people in shelters at the end of the year to be in the unafflicted category. Shelters largely have 2-week time limits, so we used 2 out of 52 of annual shelter inhabitant counts. We also consider drug addicts and mentally ill people who have housing to be in the poor category. In brief, drug-addicted homeless people can stay addicted, get help through shelters, through New Year's, or die. Mentally ill homeless people can become drug addicts, remain mentally ill, or get help through shelters. Unafflicted homeless people can become drug addicted, mentally ill, stay unafflicted, or get a home and become poor. Domestic violence victims will either escape to become unafflicted homeless people or remain victims of abuse, and the deceased will remain in the same state. We can pull statistics from online to then create a transition matrix, as well as a starting vector representing starting populations in each group. We then add a vector each year reflecting increases or decreases in the population. We subtract a number to reflect newly built affordable housing that unafflicted homeless people can move into, and we add homeless children who turn 18 over the year, and homeless children have a higher proportion of drug addiction than the general homeless population. And we then add migrant homeless people whom we assume to be in the same proportions as the existing population, and we account for population growth by multiplying the populations by a value reflecting the numbers found in the first question. After writing the code snippet in C++ for Albuquerque, we were easily able to change the numbers around to get one for Seattle as well and get results for Seattle. And from our state functions, we can get estimated headcounts in every category after any number of years, and we add the 3 homeless categories to get a total number, which we can see here. And notably, Seattle, in our model, is predicted to have a decrease in homeless population, largely thanks to its large sheltering programs.
Question 3 asks us to help a city determine a long-term plan to help a city combat homelessness. For our third question, we decided to examine 3 different factors that could impact homelessness. As we saw from our second question, mental illness and drug addiction are significant factors when determining if someone falls into homelessness. Therefore, we decided to test the viability of having government policy to tackle these 2 issues. Additionally, we also decided to look at natural disasters. Natural disasters are rare and unpredictable events that wreak havoc wherever they hit. Because of this, they naturally destroy a lot of people's homes, putting them into homelessness. The first assumption we made is assuming that a natural disaster will increase the homeless population by an amount equal to 30% of the poor population. From our research, natural disasters result in a 3 to 5% reduction in home ownership. Because around 15% of the population is typically poor, and natural disasters will disproportionately affect poorer people with less options, we chose to assume that a natural disaster will increase the homeless population by an amount equal to 30% of the poor population. The next assumption we made is that for any government policy, the government can only help 20% of the homeless population per year. Pareto principle, a common rule that describes many systems, states that 80% of the outcomes result from 20% of the most important causes. In the context of government policy, this principle suggests that government effort should focus on improving 20% of the homeless population. Our third assumption is that a government policy to reduce mental illness would help 15% of the homeless population affected by mental illness per year. From our research, psychotherapy, one of the treatments that can help people with mental illness, helps 75% of the people that get it. By multiplying this with the 20% from our second assumption, we get that government policy would help 15% of the homeless population affected by mental illness per year. Our fourth and final assumption is that a government policy for drug addiction would help 8% of the homeless population affected by drug addiction per year. From our research, less than 42% of those that enter rehab for substance abuse complete the process. By multiplying this with the 20% from our second assumption, we get that government policy would help 8% of the homeless population affected by drug addiction per year. For our model, we will reuse the model from part 2, with the parameters adjusted to the impacts of the aforementioned circumstances. Since our model already deals with how these states of homelessness change over time, we thought this was a fitting model to use for this problem. Based on our assumptions, we already know that government policy provides positive changes to mental illness and drug addiction, while natural disasters will increase the rate of homelessness.
We modify the transition matrix to mirror the change mentioned within our assumptions. Each number represents the probability of maintaining the same status until the following year. The government policy affecting the mentally ill can be seen on the right. The probability reduces from 71% to 56%. Additionally, there's a 15% increase in the chance that someone who is mentally ill can escape homelessness and enter a state of poverty instead. Similarly, a positive change can be seen on the left reflecting government policy for drug addiction. The decrease from 71% chance of stagnation to 63% chance in conjunction with an 8% change of escaping homelessness. We will assume that a major natural disaster strikes in 25 years into the future. Halfway through our simulation, when the natural disaster strikes, we will increase the homeless unafflicted population by 30% of the impoverished population. For the cases without a natural disaster, we can see that a policy to combat mental health problems was the most effective. However, in the situation where a natural disaster does occur, homelessness increases significantly. There's about a 27% increase between no natural disaster and natural disaster for no government policy, 28% for mental health policy, alongside a 29% change for substance abuse. Thank you.
Great, thank you. So we have some questions from the judge panel.
I have a question. Thank you very much for your presentation. You had your first state function model slide when you introduced, you had your various categories, and there was one that was, the one that had debt as one of the categories. Can you explain to me, unless I misunderstood, there was no category where people exited into being housed. Can you talk to me about that a little bit, or?
So we consider homeless people who are able to afford housing. We put them into the poor category because while they do have housing, their income is still probably not very high, and they're still at a risk of losing their home. So,
Right. So, all right, people, okay, so they went into the P category. Okay, all right, thanks.
You have a question?
Yeah, I do have a question. I think I'm on. For your Markov chain, I did see one of the final slides was about the transition matrix, how you adjusted it. Could you explain one more time, how did you come up with the transition matrix probabilities before you adjusted this?
So the probability before was based off our assumptions, and it's the same state function model that we used in the second assumption, and so the numbers that we got were reflected across.
Where did you get those numbers from?
so we found various sources that said things like the percentage of whatever demographic that becomes whatever other demographic, and some of them we found that the average duration of homelessness is 40 months. So, for example, for the chance for an unafflicted homeless person to get housing, we used the number of unafflicted people who get housing, and then we multiplied it by 12 over 14 for the 1 year.
So you compiled different sources to get the transition matrix? Is that right?
Yeah, so basically we looked through sources like SAMHSA was a big one, like psychiatry.org.
Just curious, were there any inconsistencies? You have 6 different states and you're looking for, that many probabilities. Any inconsistencies is in the data because your probability should add up to 1. What if different sources have contradictory probabilities? Was that a case?
Yeah, so we did have that happen, and so what we did was we found the average of all the sources, and so we tried to compile as many as we could, and
Okay. Okay.
I had a question about part 1. So you guys used a random forest regression model, which we've seen some teams use, and you identified that one issue with these sorts of models is you typically need a lot of training data, which wasn't necessarily present in the data set we gave you. What would you do if you had more time and you could collect more data? How would you get more data for that type of model? Because one thing we found is there's not necessarily reliable homeless data going back, that many years. So is there anything you could do to make up for that?
Right. So what we did was we took the previous 13 consecutive years. However, it's not necessarily a necessity for it to be consecutive. So for any year that we could find for data for Seattle or Albuquerque, we could take that data on homelessness, population, and median income, because we made sure that the factors we used were data that were commonly collected and stored on government websites.
So did you use the same model? Is it the same model for Albuquerque and Seattle?
It is the same model, however, we trained them on the respective data for each city.
Okay. Because I could imagine one way of boosting data is you include more cities. Is there a reason to do a different model for different cities? Could you use data for other cities besides Albuquerque and Seattle to help with this data problem?
We found that the patterns for each respective factor, for example, population, median income, and unemployment rate, had different effects on the housing supply for those cities. This could be effects of possibly location, region. However, we had to make sure that these models were reliable for those cities specifically.
Okay. Okay, makes sense. Any questions? Yeah.
Yeah. So in question 2, you mentioned that you made predictions for Albuquerque and then you modified the numbers to make predictions for Seattle. Could you explain how that was done?
So basically, we have our starting vector and our transition matrix, and our we have another vector that we add in each stochastic step, and that's just really big ugly piles of numbers in the C++ thing, and we just we found a list of data and sources first, and then we just shifted the for example, in Albuquerque, there's a slightly higher drug addiction rate. So there would be in Albuquerque, the probabilities of an unafflicted homeless person becoming drug addicted would be higher. So we would shift it accordingly in the transition matrix for Seattle when we made a new program.
Thank you.
Okay, maybe we'll wrap it there. Thanks, guys.